Todo cerrado, debería funcionar esto. Vale.
A ver si funciona.
No.
En principio todos los participantes tienen opciones. A ver, opciones de la reunión. Opciones de la reunión.
Ya se ha iniciado la grabación.
Sí, se ha iniciado la grabación. Todos pueden omitir la sala de espera. Todos pueden presentar todos. ¿No funciona la opción de compartir?
No. No lo consigo.
A ver. Es el cuadrado, es ese cuadrado con la flecha que hay hacia arriba.
Sí, lo estoy dando, pero pone escritorio y ventana o Freehand by Vision.
Puede poner con escritorio, verá lo único que se verá su escritorio, que es mejor. Tiene que haber una opción que le permita compartir el PowerPoint.
Sí, es lo que estoy intentando. Luego habitualmente, ¿no? Pero,
bueno. Sí, no, me imagino, pero bueno.
Sí. Ahora parece que se ve.
A ver.
Aquí, compartir. No.
Sí, ahora sí. Sí, lo único que hay que seleccionar el PowerPoint ahora. Ah, muy bien. Vale. Sí, se ve. Vale, pues si puede. Vale. Sí. Bueno, pues.
Vale.
Vale. Bueno, pues voy a hacer una pequeña introducción y empezamos entonces. ¿Ok? Okay, sorry for this short delay. Good morning, everybody. We are going to start the second session of the course on renewable energies, energy efficiency, and technical change. As Professor Meya pointed out yesterday, the course is organized within the framework of the Civis Consortium, made up of 9 European universities, Aix-Marseille Université from France, National and Campo-Distrian University of Athens in Greece, the University of Bucharest in Romania, the Université Libre de Bruxelles in Belgium, Sapienza Università di Roma in Italia, and in Italy, and Stockholm University in Sweden, and the Eberhard Karls University in Germany, the University of Glasgow in Scotland, Universidad Autónoma de Madrid. In addition, the Jamonet Amenet Network for the Integration between Africa and the EU collaborates in the organization. Amenet Network is integrated by 14 universities from 11 African and European countries, France, Poland, Greece, England, Morocco, Mauritania, Senegal, Cape Verde, Ghana, Democratic Republic of Congo, and Spain. And this network is financed by the European Union through Erasmus Plus Fund, and it includes research actions, teaching and knowledge diffusion, and paying special attention to young researchers. And finally, collaborating in the organization, we have also ECOWAS Center for Renewable Energy and Energy Efficiency, and CERMI, the Center for Renewable Energies and Industrial Maintenance. So welcome everyone to this second session of the course, especially those attendees who yesterday had problems with the connection and who are joining the course today. As I reminded you in the messages, I sent you that the first session is available on Microsoft Teams page of the course. Within the files section, and you have a folder with the recordings of the session. Yesterday, I received some messages saying that some of you could not access the recording, and the problem is because you have access in the course not as students through Microsoft Teams, but using the link that we have sent by email. This link is a kind of backdoor or emergency door for the course. And if you want to have full access to the course, full access to the materials and the recordings, you must access using the email you receive directly from Microsoft Teams, clicking the blue square or the blue button that appears in that email. Although I think that some of you have had problems even with this link. In addition to all those who have entered today using a link and not the automatic mail of Microsoft Teams, we ask that please write your name and surname in the chat to be able to control your presence, since the application does not allow us to easily identify those people who enter through that access, especially if you are using a different email than the one you sent us in the registration form, because we could have difficulties with attendance certificates. So if you have any problem, we ask you not to expose it now, but write us an email, and we will try to solve it as soon as possible. We know that you have had many difficulties, but we will try to solve all of them. Well, before introducing the speakers for today's session, I would like to briefly recall the two presentations that were made yesterday, especially for those who were not able to follow the session. The first presentation was made by Dr. Solvet Carbuz, who was talking to us about the energy prospect in the Mediterranean countries in a time frame of the next 30 years, and also about the possibilities and need for cooperation. Among the conclusions reached, I would like to highlight that current policies will not be enough to reduce energy demand and to mitigate CO2 emissions. And the challenge is not only climate change, but also the energy dependence of the region. Another conclusion is that we need a Euro-Mediterranean Green Deal to promote the energy transition and exchange of best practice and know-how. And finally, the recognition that all technologies and policies will be needed to reduce CO2 emissions. And in the second presentation, Dr. Luis Arribas was explaining to us from a technical point of view, the different wind generation techniques and their possibilities, both at large scale, like wind farms, and on a smaller scales. Wind energy is in fact one of the most widely used renewable energies, but it should have further development in the coming years, precisely because it's a very advanced technology with relatively low cost. In today's sessions, we will discuss two additional renewable energy sources. The first is a more innovative, or at least more unknown, as is the case of renewable hydrogen. And for this issue, we will have the intervention of the engineer Juan Puertas. And next, we will deal with a relatively better known energy, but not less important, such as the use of biomass. These presentations will be made by Professor Salim Belsayed from Stockholm University, one of the Civis universities. So as not to delay any longer, I'm going to give the floor to Juan Puertas. As you know, you have around 50 minutes to allow a final time for questions for the attendees. So, Juan, the floor is yours.
Okay. Thank you very much, Mr. Collado. It's a pleasure to me to be here with you, speaking about hydrogen. You can see the screen?
Not yet. No. You were sharing before, but...
No?
No.
Compartir, ok.
A ver.
Theoretically, yes.
Now, yes, now you're sharing your screen, and now you have the presentation. Okay.
It's okay?
Yeah, yeah, now it's okay. You can try with full presentation. It's okay.
Okay, perfect. Now we can ask why we speak about hydrogen in a session in a seminar about renewables. The question is very clear. When the press, the universities explain how to avoid the CO2 emissions, the answer is always the same. It's necessary to electrify the economy. That is true, but it's possible to electrify the houses, to electrify the offices, the universities, the tertiary sector, but it's not possible now to electrify the heavy industry, the industrial processes with high temperatures. It's not possible to substitute fossil fuels in long-distance transport, in planes, in boats, and these activities, heavy industry and transport, consume approximately 55% of the fossil fuel around the world, and there are no solutions. Electrifying the economy, electrifying the houses, we can avoid the 45% of the CO2 emissions, but it's necessary to look for a solution for the other 55. And it seems that hydrogen could become the substitute of fossil fuels. If we speak about hydrogen, hydrogen is the most abundant element around the universe, but unfortunately, it's impossible to find free it in our planet. There are no hydrogen free. The hydrogen is present in a lot of compounds, water, hydrocarbons, carbohydrates, a lot of compounds, but is not free. And to obtain hydrogen, it's necessary to split a molecule that contains it. For example, water, methane, and other molecules. And it's necessary to give energy to split this molecule. Okay. One very good characteristic of the hydrogen is the high calorific value. It's the highest calorific value by unit of mass in the elements. One molecule of hydrogen contains 142 megajoules a kilogram of hydrogen contains 142 megajoules. But on the other hand, is the lightest element. 1 cubic meter of hydrogen weighs only 19 grams. It is very difficult to move a gas with this very low density. It's very complex to move. Hydrogen, for example, has 3.5 more density by unit of mass than petrol or natural gas. It's very important to remember that hydrogen is not a fuel, it's a carrier. To produce energy, it's necessary to give energy to the molecule to split the molecule. Hydrogen takes this energy and gives us the energy when we return to join hydrogen with oxygen. In the moment that we isolate hydrogen, hydrogen retains the energy and gives us the energy with this oxygen is joined with another particle of normally of hydrogen. Hydrogen can be used in a lot of applications. We can use in fuel cells. We speak in a minute what is a fuel cell to produce electricity. We can oxidize the hydrogen in conventional burners to produce heat, or in turbines to produce mechanical energy. And finally, we can react in hydrogen with carbon monoxide to produce synthetic fuels. And this is a very big way that you can explain in advance. We will speak about today. People speak normally about green hydrogen, but there are a lot of other types of hydrogen. Depending on the energy that we use to split the molecule, we can obtain different types of hydrogen. If we use fossil fuels to split the molecule, we can obtain turquoise hydrogen or blue hydrogen. If we use renewable energy, we can green hydrogen. If we use nuclear energy, we can obtain red or purple hydrogen. All these types of hydrogen, turquoise, blue, green, red, or purple, there are hydrogens without emissions of CO2. Take care a moment. If we use fossil fuels, if we use natural gas, for example, and we use a process of pyrolysis of this gas natural, we obtain hydrogen, turquoise hydrogen, and solid compounds of carbon, graphene, of diamonds, depends on the pressure of the process. And this process is very interesting because the subproducts that we obtain are very high value in the market. Obtain hydrogen and graphene, for example, is a very good result. We can use natural gas too, but doing stream reforming. We can do an stream reforming with natural gas with vapor with water in form of stream. We do a reforming process and we obtain gray hydrogen. This is the way to obtain hydrogen now around the world. The 90% of hydrogen now is gray hydrogen, but the gray hydrogen have a problem. Each kilogram, to produce 1 kilogram of hydrogen, we produce 11 kilograms of CO2. This process of reforming is very intensive in production of CO2, and is a problem. But we can do the capture and sequestration of this CO2, or we can storage the CO2, and if we storage the CO2, we obtain blue hydrogen, and is another form to have hydrogen without emissions of CO2. If the raw material is coal, in the same process, we can do petrol to the steam reforming. We do coal in the gasification, and in this process, gasification coal, we can obtain brown CO2. This brown CO2 is necessary to do the storage or the sequestration of the CO2 to obtain blue hydrogen. Finally, we have all the possibilities to obtain green hydrogen. We can use biomass, gasification of biomass. You know, the gasification of biomass do emissions of CO2, but these emissions are a circle, and the CO2 is reabsorbed by the planet, and is neutral in emissions. We can do processes more complex, like biophotolysis, than directly the biomass with the biophotolysis permit obtain green hydrogen. The more common to obtain green hydrogen is to use aeolic or solar energy to produce electricity. This electricity with water, at electrolysis, we obtain green hydrogen. This is the process more common, the process that we speak in this presentation. But it's possible to use directly the solar energy, the light of the solar energy and water in a photoelectrolysis processes, or the heat on the solar panels in a thermolysis process to produce green hydrogen. This is possible, but in this moment more expensive than the electrolysis. And finally, we can use nuclear energy than source of energy to give this 142 megajoules to the hydrogen, and we can use the heat of a nuclear power plant with water in a thermolysis process to obtain red hydrogen, or we can use the electricity of nuclear energy in electrolysis, like the green process, and we obtain purple hydrogen. All these 5 types of hydrogen, I repeat, are free of emissions. Okay, simplifying, you can read in press, you can read in that there are 3 types of hydrogen. That is a simplification. Gray hydrogen, split in natural gas into CO2 of hydrogen, and the CO2 is emitted to the atmosphere. Blue hydrogen, that is the hydrogen that we obtain if we storage this CO2. Finally, green hydrogen, split in water into hydrogen by electrolysis, powered by wind and sun. This is simplification, but the reminder that there are a lot of other forms that produce hydrogen. There are the forms that you have in the previous table. Okay. Electrolysis. The electrolysis is a process that permits split the water molecule in oxygen and hydrogen. If you circulate electrons by water, these electrons into the water, the ionization of the water, and the ions oxygen can join it in the cathode, and the ions hydrogen produce molecules of hydrogen in the cathode. And this process has an efficiency about 85%, and we will need 45 kilowatt hour of electricity to produce 1 kilogram of hydrogen. 45 kilowatt hours are approximately 160 megajoules, because it's more than 142 that we will need in an ideal process, but with the 80% of efficiency, we need to increase this quantity of energy to complete the process. Okay, it's very simple, and I suppose that you know very well the electrolysis process. What can be done with green hydrogen? Okay, with green hydrogen we can solve a lot of problems that now we solve with fossil fuels. If we have renewable electricity, we put this electricity in an electrolyzer, and we produce hydrogen, green hydrogen. We can put this green hydrogen in a pipe to move this hydrogen with pressure, and we can add to this pipe hydrogen produced, for example, blue hydrogen, or we can put green hydrogen produced by biomass, for example. We can produce the hydrogen in other countries, in other areas, in other places of the world, and move by boat, liquefied, and introduce this hydrogen in this system, for example. No? We can use hydrogen in buildings to substitute the natural gas in building, because I have the opinion that there are better solutions than hydrogen for buildings. We explain in advance, but it's possible to substitute natural gas as fuel in buildings, in normal appliances. It's possible to use this hydrogen in high-grade heat processes with high temperature, for example, in steel production or concrete production plants, or paper plants, or the heavy industry and the petrochemical industry, for example. All these sectors, we can substitute fossil fuel for hydrogen, and the hydrogen can be used like feedstock in the chemical industry, for example. Okay, and finally, we can solve all the problems in transport with hydrogen. We can move planes with synthetic fuels produced by hydrogen, join hydrogen with carbon monoxide. We can use directly the hydrogen in heavy duty, for example. We can use fuel cell vehicles, or we can move trains with hydrogen, or we can use in the shipping industry. We can use both moved by ammoniac produced with this hydrogen. And other application of the hydrogen, we can storage this hydrogen in tanks, for example, and we can use this hydrogen in a fuel cell to produce electricity. We can produce hydrogen in the night, for example, when we have excess of electricity. We can produce electricity with hydrogen in the peaks of demand. For example, now is a moment that all the network around the Europe, for example, is in a peak, and we could produce electricity with hydrogen now and complete the system. Okay. And finally, we can blend this hydrogen and with natural gas, introduce this hydrogen directly in the natural gas network and reduce the emissions. And this gas grid can go to the industry and reduce emissions in the average that we mix this hydrogen with natural gas. This is a fuel cell. A fuel cell is the opposite of electrolyzer. If we introduce hydrogen in a fuel cell, the protons cross the core, the hearth of the fuel cell, and this green are the protons. The electrons are outside the circuit, and in the cathode, the protons and the electrons joined with oxygen that we introduce for this air, for this area. We introduce air. The oxygen of this air joined with the proton, the electron of the oxygen, producing water stream, water vapor. And the electrons go to the circuit that we produce electricity here. The efficiency of this technology depends on the technology, and there are 5 types of fuel cells. We can group these fuel cells in low temperature fuel cells and high temperature fuel cells. There are 3 types of low temperature fuel cells. The membranes, the hearth of the fuel cell is a membrane, a specific membrane. This type is the more simple type of fuel cell. This fuel cell works at a temperature of 100 centigrades, has an efficiency about 0.42, 43 approximately. The second group of low temperature fuel cell are alkaline fuel cells. The hearth of the fuel cell is hydroxide of sodium, and the protons cross this solution of should cross this solution of hydroxide of sodium. This fuel cell works at 200 centigrades, about 200, have an efficiency of 0.47 approximately. And finally, in the low temperature fuel cells, we have the phosphoric acid fuel cell, that the hearth of the fuel cell is acid of potassium. Okay. This fuel cell work at 350 centigrades and have an efficiency about 50%. And in the group of the high temperature, we have 2 types. Molten carbonates. The hearth is molten carbonates. To have these carbonates in liquid state is necessary to work at temperature between 700, 705 centigrades, and we cannot time an efficiency of 0.65. And finally, we have solid toxic fuel cells that go on more of 1,000 centigrades and achieve efficiencies up to 70%. Why this high temperature fuel cell has more efficiency than the low temperature? Because we can configure these fuel cells like cogenerations or like combined cycles. We can use the fuel cell like a low temperature fuel cell, and with the head that we have it in the cathode, we can produce steam in a steam boiler, and we can obtain an additional part of electricity in a conventional turbine of steam, okay, in both cases. The price increase with the temperature, with efficiency. It's possible to obtain now fuel cells about the 700 dollars kilowatt in low temperature, and in oxide solid fuel cell the price is the $5,000 by kilowatt. Okay. These are all the solutions that we can solve with hydrogen. We can we can solve all the problems of transportation. It's possible to have trucks with hydrogen. It's possible vehicles for urban transportation with hydrogen. It's possible to have trains, boats for kids, for industry, planes with synthetic fuels. For all the transportation, there are solutions with hydrogen. For all the houses too. But as you said before, in my opinion, in the houses, in the buildings, it's better to electrify the buildings or to use biomethane. Tomorrow you have a session with biomethane. In my opinion, biomethane is a better solution for buildings than hydrogen. And finally, in the industry, all the high temperature processes have solutions with hydrogen, and hydrogen should be green hydrogen can substitute gray hydrogen, like festook in the industry without emission. The total emissions, annual emissions in the 2019 around the world were 37 gigatons of CO2. Past year was 34 because the effect of the COVID reduced the emissions around the world. But approximately we are moving in the last years around the 36 gigatons by year of emissions. With hydrogen, we can avoid the 55% of these emissions with applying these solutions. And the other part that we cannot solve with hydrogen, we can solve electrifying the economy, the other 45, because the union of electricity and hydrogen could solve the problem of emission around the world. But you can ask why we cannot apply the solution quickly? Because if the join of renewable energy and hydrogen can solve the problem of emissions, why we not change the model? Well, the problem is the price. The price, because in this table you can see when the solutions with hydrogen can be competitive with the traditional solutions. For example, the first, regional trends. It's possible that in 5 years, trends moved by fuel cell can substitute diesel trends if the solution, the alternative were to electrify the line. If we need to take the decision, use trends with fuel cell or electrify lines that use diesel, it's possible that in 2025 the solution with fuel cell will be more competitive. It's the same with heavy-duty trucks. Probably we can see heavy-duty trucks in the motorways of Europe in 5 years. Why? Because the price of hydrogen, if we need to pay the emissions that we do with diesel trucks, will be cheaper. The solution with hydrogen, and we have here for all the solutions that we can have seen in the previous one slide, when can be commercials. No? There are processes, for example, in the heavy industry, to produce ammonia or to produce steel, for example, or the petrochemical industry, that green hydrogen is now competitive. And all the petrochemical plants in Europe are changing the production of gray hydrogen to green hydrogen, because I say in starting this presentation that to produce 1 kilogram of gray hydrogen, we emit 11 kilograms of CO2. The ton of CO2 in this moment is the cost is 60 euros by ton. If we need to pay 60 by 11, we are paying 66 euros by ton of hydrogen. With this price of CO2, it's better to use electrolysis processes and change the production with steam reforming, for example. Okay. With this table, we one side that we can be in the future, in the next years, more and more applications with hydrogen. Well, this table is the same. This show the applications that we will see more quickly. For example, regional trends or heavy-duty trucks. For example, the more commercial in this moment. Well, the price of produce green hydrogen in this moment is about $30 to $60 by kilogram, and the objective is to arrive to between $3 or $7 by kilogram, put in the place to use it. With this band of prices between 3 and 7, green hydrogen could be competitive with petrol, for example. Okay. Well, this is the future of the mobility. The mobility with about 100 kilometers and less of the 10 tons of weight of the vehicle will be electric. In the future, all the cars in the cities to move around the cities will be electric. In the medium longs, between 100 and 1,000 kilometers, we will be mobility with hydrogen. Trains, trucks, buses, intermediate buses, taxis will be by hydrogen. And in the long transport, more of 1,000 kilometers, and if the vehicle has a weight of more of 10,000 tons, the solution will be synthetic fuels. Synthetic fuels produced with hydrogen. Okay, you join hydrogen with CO2 or hydrogen with monoxide of carbon using Fischer-Tropsch, Sabatier, or all the processes that permit to obtain synthetic fuels. Okay, but all the mobility up to 100 kilometers will be moved by hydrogen directly or with synthetic fuels. How is a car with hydrogen? Is very easy. You substitute the conventional engine of petrol by a fuel cell, normally a membrane fuel cell, the more simple of the low temperature fuel cell. You install here a electro engine, and you install a small battery because you produce the electricity inside the vehicle. You move this electricity to the battery. If you have the battery, you can take advantage of the energy of the braking, for example. You can obtain another advantage in the vehicle, and this electricity of the battery move the electro engine. It's very simple, very simple concept. And you have a tank of hydrogen. Normally, a car as using tanks of 5 kilos of hydrogen at 700 bars of pressure. And with this quantity of hydrogen, you have an autonomy of 750 kilometers. Okay. There are two types of cars, commercial cars in this moment with hydrogen. You have the Toyota Mirai and the Honda Clarity. Toyota Mirai is the more common around the world. In California, for example, there There are thousands of these cars, and the state of California give the hydrogen free for all the people that buy one of these cars. The only problem is you need $80,000 to obtain one of these types of cars, but are commercial. This is the same for trucks. This is the Hyundai Xeon. In Sweden, for example, in Switzerland, excuse me, in Switzerland, it's obligatory for all the public trucks, the trucks that work for the municipalities or for the policy, for example, it's obligatory that be hydrogen trucks, and there are 1,500 cars in Switzerland of hydrogen. This is the model very common in the United States, the Kenworth T680, that to join some state, for example, California and Nevada, is obligatory that to move products between these two states, the use of zero emissions trucks like this. This is a trend produced by Alstom, a French company, that is moving for Saxony in Germany, in Saxony, and there are trends moved by hydrogen in lines without electrification, for example. And well, there are some examples. I will speak about the hydrogen like solution to advance in renewables. For example, we can imagine if we need to promote a wind farm of 100 megawatts. The investment that we will need is about $140 million. We have here the unitary cost of the technology now, and we can produce with the wind farm 250 gigawatts hour by year. Okay, but we only can solve the 80% of this energy, because we will produce energy in the night, electricity in the night, with the demand will be less of 100 megawatts, for example. And we will lose in this process 50 gigawatts hour by year. We have an income selling this electricity of $12 million by year, and we have a payback on approximately 12 years of payback. Okay, if we join electrolyzer of this wind farm, electrolyzer of 20 megawatts approximately, we increase the investment in 10 millions. We have 150 millions of dollars. We have the same electric production. We sold the same quantity of electricity, but we can use the 50 gigawatts hour we lost in the previous case to produce hydrogen. And we can produce 1.11 tons by year of hydrogen. Excuse me, million tons. There are a mistake here. It's 1.11 million tons by year. I will change this mistake in the presentation. And the annual income, we increase the annual income selling these million tons of hydrogen at $3 the ton, and the new incomes are 15.33. And the payback now is about 10 years, 2 years less than in the previous case. The hydrogen can be as effective solutions to not sell electricity in the wind farm, for example. Okay, and if we dedicate a photovoltaic plant, dedicate only to production of hydrogen, we have here the figures, and the payback of a photovoltaic plant dedicated only to the production of hydrogen will be only of 8 years. Okay, this is very interesting. For example, in Africa, in the north of Africa, is a special point to produce to install photovoltaic plant dedicated only to produce hydrogen. Well, we are finishing. We speak to finish the new geography of energy. In the beginning of this cycle, the United States was the leader of consumption of energy. with approximately 2,500 million tons of oil equivalent. The second was European Union, and the third was China. And Africa was the fourth, but the demand of energy of Africa was less of 500 million tons of energy, 5 times less of United States. And this photograph, the people say that this photograph don't change a lot during the years. But if we take the forecast for 2040, we have here, in 2040, China will be the main consumer of energy with approximately 4,000 of million tons oil equivalent, the double of United States. United States will be in about 2,000 million tons of oil equivalent. India will be the third, and Africa will be the fourth. Africa in 20 years will consume more energy than European Union. That will be the fact. This show that Europe is reducing their presence in the energy map, and other areas of the world like Africa and China clearly and India are increasing their presence. It is very important because Africa will need a lot of investment in energy to achieve this position, and this energy will be renewables. The investment will be in renewables, and the complement with hydrogen could be essential to develop these renewables in Africa in the next 20 years. As you know, Europe has decided to be free CO2 emissions in 2050, and but this is not an easy travel. This is not the consumption of primary energy in 2019, as you can show in the previous slides, was about 2,000 million ton oil equivalent, and the 74% of this energy was fossil fuels. To substitute these fossil fuels is not an easy task. For example, the consumption of natural gas in this year was about 20 exajoules, 475 BCM of natural gas. If we want to substitute this natural gas by hydrogen, will be necessary 250 megatons of hydrogen by year. And to produce this hydrogen, we will need about 6,870 terawatt hours of the year of electricity. Well, this we're speaking about very big quantities of energy. To produce this quantity of electricity with turbines of 6 megawatts, the biggest in this moment, we will need 500,000 machines, and we will occupy the 10% of the surface of Europe. This is impossible. It's impossible. It's clear that Europe will need other countries, other areas of the planet to do this transition. And the natural partner of Europe is Africa. In the future, Europe will need Africa to develop their policies of free emissions. And Africa will be an exporter of renewable energy, electricity energy to Europe, and especially to export hydrogen to Europe. In this map, you can see the distribution of the cost of production of hydrogen around the world. As you can see, the red areas are the areas with the produced hydrogen is cheaper, and the blue areas are the areas that are more expensive. And you can see the majority of Europe has very high price to produce hydrogen. Why? Because the efficiency of the renewables are less, a few quantity of hours to produce renewables, and the efficiency of the process is less. Only Spain Portugal, the Iberian Peninsula, the Iberia Peninsula, and Italy has medium conditions. But you can see Africa had an excellent position, because some areas of Africa has a very high price under $2 by kilogram of hydrogen. This reinforces the idea that Europe will need Africa to do the change. And there are cases like Russia, that will be impossible to produce green hydrogen, or Indonesia, for example, or Japan. In the case of Russia and Indonesia, that have big quantities of natural gas, it's possible that Russia and Indonesia decided to produce turquoise hydrogen. Turquoise hydrogen, remember, is the hydrogen produced by pyrolysis of natural gas. Okay. Well, finishing. 2 years ago, Siemens installed in Australia the first big plant to produce hydrogen with 15 megawatts of electrolyzers. And the CEO of Siemens in Australia Pacific region said that Australia has potential like no other country in the world for hydrogen production and export, as long as we act upon the opportunity quickly. This man imagined exporting West Australian sunshine and wind to the world in the form of hydrogen. Well, with this presentation, I want to transmit to you that I think that Africa has, as minimum, the same potential that Australia, and I imagine Africa producing renewable energy for Europe in the next years. Okay, thank you very much for your kind attention, and it has been a pleasure.
Okay, thank you very much for your intervention, and now we open the questions time to attendees. If there is anyone who wants to ask any question. Is there any question? You can open your microphone and ask directly if you want.
How extensive is the hydrogen pipeline in different parts of the world? So I'm guessing that to transport hydrogen from one area to another area within each country in Africa or Europe, you need to actually create a pipeline independent of that of natural gas, right? So how does that look in terms of pricing, infrastructure, and how much time will it take to build that out?
Okay, now to move hydrogen is the big problem of the industry of hydrogen. The more usual form to move the hydrogen is like natural gas with pipes, by pipe, compressing by pipe. To move hydrogen from Africa to Europe will be necessary to build infrastructures, pipe that connect in Africa and Europe. We can use the same pipes that now move gas and oil, for example, from Algeria to Spain or to Italy, or build a new pipelines. It's possible to move this hydrogen liquefied by boat. This process is more expensive, but in the future it's possible that reduce the price of this the liquefaction of hydrogen and move by boat, similar to natural. And finally, there are another processes by absorption with some products. It's possible to move the hydrogen in ammoniac, move the ammoniac, and when you receive the ammoniac, you can split another time in nitrogen and nitrogen. There are some forms, but the more simple and the more commercial in this moment is to move by pipe. And the price that to the hydrogen to substitute natural gas in the industry, for example, the price of natural gas should be the price of hydrogen should be the cost of production and transport, not up to $3 by kilogram. If the price is higher, it's impossible to substitute natural gas by hydrogen in the industry.
Mm-hmm. Okay, thank you. There is another question in the chat. It says, it's from Shalin Wu. It says, Japan holds the vast majority of the patents for hydrogen vehicles, but it's seen that car companies like Honda and Nissan have given up on producing hydrogen vehicles. How do you think this? How do you think about this? Thanks.
Well, no, it's not true that Japan has all the patents of the fuel cells. In this moment, there are patents in Europe. In United States, there are a lot of patents for the 5 types of fuel cell that I say. It's real that for the moment, in Japan, Japan take advantage to produce cars by fuel cells. The Toyota and Honda have an advantage of 10 years producing commercial vehicles. At this moment, all the big producers, BMW, Mercedes, Audi, are producing, are developing cars with fuel cells. And in 10 years, I think that all the big brands will have cars with hydrogen. It's a line, but the car is not the segment more important for the transport. The trucks will, the 100% of the trucks in 20 years will be by fuel cell, but not the 100% of the cars will be with fuel cells. Only a few parts, because the electric car, in my opinion, have advantage in the medium and long, in the medium distance. Only the cars that move more than 1,000 kilometers will be with hydrogen.
Mm-hmm. Okay. Any other question?
Yes, there is a question. Yeah. I am Boudou Miranyo Jean from Université Évangélique en Afrique. And I have a question. According to the presentation of the professor, it is said that African countries are going to consume much more energies than Europe in 20 years coming. Mm-hmm. So and you said that Africa has a big potential to produce hydrogen. So my question is, so how do you think that Africa will be able to produce hydrogen when there is no infrastructures for producing such energies? And but I've also seen there is in the chart that you have presented, okay, that some hot countries, okay, have much more potential to produce hydrogen. So is that true, or maybe because if I look in the presentation, some countries like DRC, Democratic Republic of Congo, okay, the potential of producing hydrogen is low according to the charts that you have presented. So is how can Congo, okay, for example, do to produce hydrogen with few costs? Thank you.
Well, I don't know exactly the problem with the Republic of Congo. All the area up to the Ecuador have very good conditions. Probably Congo, the price will be 1 cent of a dollar higher than other countries. So Africa will need. My point of view is in the next 10, 20 years, Europe put a lot of money in Africa to develop renewables. Okay, because Europe need energy produced by renewables. The complement of the renewables will be produce hydrogen to take all the advantage of the energy that we cannot use in Africa for this renewable. And the areas next to the coast will have more potential because we need to produce hydrogen, renewable energy, and water. And the water in Africa in this moment is a problem. You need to put near to the Atlantic Ocean to obtain this water. And in the next 20 years, the development on renewables and hydrogen will be around the coast of Africa and the Atlantic, I think, in my opinion. And maybe in the north from Algeria, Libya, in the coast with the Mediterranean. And excuse me. In the second part of this cycle, we have development in the center of Africa, but the natural evolution will be in the coast, and in these areas will be the major opportunities to develop renewables and hydrogen.
Thank you so much.
Okay. Thank you, Mr. Puertas, for your intervention.
If there are more questions, if the people can send to you and you send to me, and I promise to answer all the questions if you want. Okay, thank you very much.
Thank you. Okay, thank you. We will continue with the second session. Professor Salim Beljazid, are you here? I think you're here.
Yes. I am here.
Ah, okay. Okay, thank you. Good morning.
Good morning.
Okay. You can share your screen if you want.
Yeah. Thank you.
We sent the 3 documents to participants. Okay.
Right.
Yes, perfect. Yeah. Thank you.
Do you hear me okay?
Yes.
Yeah, good. So
Yes.
first, thanks to Jose and Luis for organizing this. And it's nice to see so many people around, and I have actually no idea where we're all sitting. I think if we calculate the maximum distance from the ones who are furthest, I would be impressed. And it's nice to hear such a different background of lectures, and I hope this will be somehow useful when we change the context. So please don't hesitate to interrupt if you want. This is not, I would rather not have it as a monologue. So interrupt me anytime you want, and you have to speak a bit loud because I get carried away with my own voice. So what I will talk to you about today is something I got a little bit inspired by this book by Isaiah Berlin about the hedgehog and the fox. And there is, at least in North Africa, in Morocco, where I am from, there is a similar story when we were kids that our grandparents used to tell us about the hedgehog and the fox, very much in line with Isaiah Berlin's book. And this story is about the fox and the hedgehog who go into a chicken cot and through a little crack in the wall, and they start to eat chickens and eggs. And the fox goes and tries if he can go out all the time, so he doesn't eat too much and get stuck, but not the hedgehog. The hedgehog keeps eating. So in the morning, the farmer comes and the fox can sneak out through the crack, but the hedgehog gets stuck. And the idea with this is, so what this essay by Isaiah Berlin is about is, in the view of Tolstoy of history, there is only one way history can develop and one way forward. So a little bit like the hedgehog behaves. We're here just to eat, so we eat everything we can without thinking about what can happen in the future. The fox is a little bit more about adjusting goals and seeing what works as we go. And this is the concept I want to apply to the way we're dealing with forestry in Sweden. And I hope I can succeed in telling you a little bit about that. Are you anything familiar with this donut concept? I know, unfortunately, I don't see you guys, so I'll just guess the answer I want to have, and that's, yeah, we're familiar with it. So good, we're familiar with this. And what it is about is we have the planetary boundaries. And if you haven't been in touch, if you don't know the planetary boundaries, there is a very interesting documentary on Netflix, actually, about the planetary boundaries. And they show us 9 pillars of ecological sustainability on the globe. And these are the boundaries within which we can use nature without breaking it down. And there is a Dutch economist who, within these 9 boundaries, has put the needs of people, the things we need for our own survival and welfare, food, water, basic things, but also things like jobs, energy, which we will be talking about today, but also things like equity, education, gender equality, resilience. And between this, what we need, and the boundaries that we have this safe space for humanity to operate, this green donut. That's where the donut concept comes from this green circle here. Now, unfortunately, we have been very good at pushing this donut outwards, and we have broken some of these planetary boundaries already. Now, I had hoped we would do breakout rooms and discuss this, but I just want you to take a little moment and think about these 9 planetary boundaries and see which ones of them you think are the ones that we have broken. So the first planetary boundary is climate change. The second one is biodiversity. 3 is stratospheric ozone. 4 is ocean acidification. 5 is biogeochemical cycles. 6, land use change. Freshwater use is 7. 8 is aerosols in the atmosphere. And 9 is new chemical substances that we put out in the environment. We don't know what their effects will be. Take a moment and think the 3 top ones that are problematic that we have broken, in your opinion. You can write the numbers on a piece of paper, and I will soon show you the assessment of the boundaries so you can compare to what you think. Okay, so I will move on. These are the 3 boundaries that we have cracked. Climate is not cracked yet. We haven't exceeded the boundary yet. And actually, the picture is not so bleak. Many of these boundaries are not broken, but some key ones are. One has to do with the biosphere integrity, and that's biodiversity. There we have already broken the planetary boundaries. We've lost many species. We have a rate of loss that is extremely elevated, and we have a very high rate of invasive species moving around the globe, pushing out other species from their endemic habitats and niches. So that boundary is broken. And the other 2 boundaries that are broken are within the biogeochemical flows, and those are nitrogen and phosphorus. And this is very much due to the use of fossil fuels that release nitrogen when we burn old biomass that is stored in oil now. It contains nitrogen, so we release that into the atmosphere. But primarily, the 2 of them in combination is because of agriculture. This is fertilizer leaching into the ecosystems. And the cycles of nitrogen and phosphorus we have affected very, very much. If you look at us now, later on when you see the participants list, more than 75% of us, so 3 in 4 people here in this audience are synthetic, including me. Synthetic in the sense that we are made of nutrients that are not in the environment in a natural way. They are there because we have access to cheap energy and cheap mines for phosphorus, energy to make nitrogen from the air and phosphorus from mines. And here we've broken the boundaries. There are limits on this because nitrogen we can make as long as we have cheap energy, but phosphorus, if the mines run out, then we will not have a lot of phosphorus to fertilize with in the scale that we do today. And this is in itself a very interesting subject to talk about phosphorus. I can go on and on about that, but it's not what I have space to do today. So these boundaries that we have broken now, I would like you to keep in mind. And then we go back to the one that we are dealing most with currently, and that's the climate one, although it's not a broken boundary yet, but we're on a good path to do it. And that is how to limit the effects on climate. And this is very much related to the use of energy. Of course, you know this, I don't need to repeat it. So in the EU, we have this global EU energy policy. By 2030, we will have 40% lower greenhouse gas emissions compared to 1990 levels. That means a lot lower than what we have in the 2000s. And we will have 20%, 27% energy that comes from renewable sources. And also, I heard the question in the earlier lecture that we maybe will be using more energy. Actually, the EU has a goal of reducing energy use, so we will increase energy saving by 27%. Not only change the composition of the energy sources, but reduce the use by increasing savings through, for example, insulation of houses here in the north, so we don't have to heat so much. So 20%, 7% of renewable energy on the EU level. When we come to Sweden, then the goals are even more optimistic. We want 40% greenhouse gas emissions reduction last year. And we are very close to reaching this target, actually. We're not very far from it at all. And by 2040, all of our electricity in Sweden will be renewable. Not a fraction of it, 100% of the electricity will be renewable. And we will have no net emissions of greenhouse gases by the year 2045, and thereafter we will go negative. So we will be fixing carbon rather than emitting. Now, I would like to draw your attention to the word. This is a legally binding text, by the way. This is a document that the Swedish government has made into a law, which means if we break it, we will have to, I don't know, probably pay a fine. The Swedish government will pay a fine to the Swedish government. But anyway, this is a law that all governments have to bind with. And net emissions means if we're not succeeding at home, we can use solutions somewhere else. And this has many repercussions somewhere else in the world. Again, unfortunately, we won't have time to go into that. But this includes solutions like carbon trading, offsetting in other countries that we plant forests somewhere else. But if we're talking about no net emissions. Now, if we're going to have this goal, 100% renewable energy, no net emissions, there are some sources to get them. In Sweden, more or less all the rivers are already dammed. So we don't have much potential left for hydropower because most of it is already used. We are increasing wind energy very much. But the main source of renewable energy is going to be biomass from the forest. If you've ever visited Sweden and you drive between cities or between the airport and a city or something, you usually drive through forest. This is a map of Sweden, and everything that's dark green is forest. 69% is... Was that a question? Okay. So 69% of the forest area, of the land area is forested. So we have a lot of forest. And most of it is actually productive forest that has been in management for the last 100 years. And it's so well managed. I'm sorry about the text here is in Swedish. I took it from the Forest Industries Interest Organization. And what this says is Sweden has less than 1%. So the percentages here on the on the x-axis. We have less than 1% of the productive forest area of the world. This is this table here. With this 1% or less than 1%, Sweden has nearly 12% of the global market of wood product export. So this is wood, like planks and stuff. So 12% of the world market and 7% of the paper pulp production and the paper pulp export, and 9% of the world paper export. So this is the pulp and this is the paper. So a large part of the global forest product market in the world, and proportionally, it is coming from Sweden. With less than 1%, we're occupying this much on the world market for wood products. And this can give you an idea how well-oiled forest machinery is, which means we have very little margins for other products. And that's what the rest of the lecture maybe will be about. And Sweden is second to only Canada in the in the exports of wood products. So over the last 100 years, what you see here is the growing stock. So how much every year, how many millions of cubic meters are growing in the forest. And for the last 100 years, there has been a steady increase in the growth of the forests. And this did not go hand in hand with an increase in area, like you may guess, that we had more open land and then we reforested it. This is just forest management. So the forest is managed in a way that we select fast-growing species, we have trenched and ditched organic soils to plant forest on them, so they would grow better. Some parts they have even fertilized, but not a lot, it's still a minimum. But it's just good practice of forest management. When I say good, I have to say very clearly from production perspective. So from production-wise, we have had management practices that allowed us to double the size, the productivity of the forests over the last 100 years. Now, when we look forward and thinking about substitution, and we're going to have 100% renewable, a lot of it's going to come from the forest. Many times in policy, we expect this line to continue. And of course, we know that is not possible. We are at the very limit of how productive these forests can be. The question is, will it crash? That's what we don't know. There was a series of studies done by commissioned by the government and maybe some through the energy agency, for example, in Sweden. They looked at a demand for biomass from forests in the future. So we will have this continued demand for the established markets for export and domestically paper, pulp, and sawmill products, wood. But there will also be other demands. So there will be demands for fuel. There will be demand for fuel and other feedstock. When this vision to move away from fossil fuels and linear economy to go into more circular economy to achieve the zero emissions, the zero net emission vision, there is a lot of work to change industries. So we want to start to use a circular model for the economy rather than a linear one. We want to move away from carbon-heavy mining, for example, and the use of metals and concrete. And all of this is going to have implications on how much we need from the forest. And already now you can see that there is more demand when we include feedstock rather than only for forest and forest fuel. In 2050, by the time we need to reach this vision, this is what we will need from the forest, this staple here. This is expressed in terawatt hours per year, so 60 terawatt hour per year is what we will be needing. Based on what we today can take from the forest, we're barely here, barely at 20. And this is if we don't want to destroy the other boundaries of these, these 9 pillars of the planetary boundaries. If we're not going to crack all of them, we have to stay within this. And this has been until now more or less a qualitative assessment. I'll tell you a little bit about it. So the study behind this pillar here, this study by Yoni de Jong and others, is based on this table here. And what it does is it uses what you see, the little icons here are the Swedish environmental objectives. We have 16 of them. And the ones that aren't gray are the ones that are directly going to be affected by forestry. And the arrows show if they're going down, it means negative effect. And this scenario here with how much intensity of forestry, that's what's represented with these numbers here in the first 4 columns. The one that has the least negative effect is this scenario here. And what this scenario tells us is in the proportion of the forest, we will be able to continue taking the stems like we did before. We use the stems then to make paper and pulp, or pulp and paper, and sawmill products. But we will also take the branches for energy production, for biorefineries, to substitute fossil fuels primarily, and also sometimes also in vehicles, for example, not only in heating and so on, and energy and electricity production. So this is the least damaging one, and it's, if I go back, you see it's way beyond what we expect. So putting a lot of hope on the forest may be not very sustainable. And now I would like to take us a little bit back down to a bit of ecology, because this is the basis of our understanding if we will know if the forest is going to be able to produce things or not. So when you think about a tree, and also me, what you think about is, branches. Now here in Sweden, the trees are changing colors, these beautiful colors and leaves, and you sit under this shade and you have this majestic large stems and branches and so on. That's actually only part of the tree. So the tree actually grows in the ground. This is a picture of a seedling. This is this thing that sticks out in the air, and it's just upside down. And this is the root system of the tree with its mycorrhizal associations and spreading out in the soil to take up nutrients and water. So the tree is actually, when you plant a seed, you don't plant it in the air, you plant it in the soil. The tree grows in the soil and reaches out for light when it comes out over the surface. So keep this in mind, that this is the living habitat of the tree, it's the soil. If we destroy this area here, we cannot sustain the biomass that we capture here. So this is what we will look at a little bit now and see if this with using the forest more is sustainable. So I want to tell you a little bit about my own research. So in my own research and the research of my group and some of my students, we work with dynamic modeling. So we try to reproduce what the forest does on the computer. So the trees will be here and they will be connected to the ground through uptake. They take up nutrients, they take up water from the soil. The trees only take dissolved things. They don't have teeth in the roots, but they pay other microbes and mycorrhizae and fungi and bacteria to break down minerals and also organic matter to provide them with these nutrients that they can take. And then all of this then is governed by the climate where the forest is, the precipitation, the temperature, and by the deposition of nutrients that the forest gets. Now, this is a very important component, the deposition of nutrients. This is when a tree is, I don't know if you have ever thought about this, but a tree is made out of air. That's the stuff that the tree is made of. An icicle, so ice cream stick is made out of water. The tree is made of air. They capture carbon dioxide from the air and then they stitch it together into carbohydrates. So when you burn a tree, the air goes back, the gas goes back out as CO2, and the solar energy that you captured in the tree during the photosynthesis process, you release back as fire. That's the energy you get when you burn. Next time you light a match, look at your match. When it's burning, that's sun energy that is released back to you. Maybe has been caught in that piece of wood for 70 years ago or something, and now it's coming back. And then you have the dust that remains, the ash. That is the nutrients that the tree has borrowed from the soil. And this is a very important component, because without this, you cannot put together these carbohydrates into wood. The Amazon is a good example, because the Amazon lives on an old soil and a soil that has not been glaciated. And because it hasn't been glaciated, it does not have fresh minerals that will provide, for example, phosphorus and magnesium and potassium and so on. So a lot of the base cations to the Amazon forest are flown with wind over the Atlantic from the Sahara Desert. And without that cloud of Saharan dust that goes over the Atlantic down to the Amazon forest wouldn't be growing the way it does now. This is an important component that we need to keep track of. When this isn't enough, that's when we fertilize. We compensate with fertilization. Now, we did look at this soil now, and so what's going on here. And in Europe, we have had this history of acidification. We burned so much coal that we deposited a lot of sulfur on our soils through this atmospheric deposition. And that caused many, many forests to become acidified. So the soil become acidic. You probably heard about this. It's called acid rain. It has many effects, not only on soils. For example, it erodes cultural heritage. You can see this on the gargoyles of churches, for example. They are eroded because of acid rain. or fish die in the rivers. Norway had a big problem with this in the 80s. But there was a convention that put catalysts on all coal-burning plants and all cars. This is that big clump that you have in the where the gas comes out in the car. That's the catalyst, and there is one inside further up in the engine that burns away or fixes the sulfur and the nitrous oxide, so it doesn't come to the ecosystems. But there was a big load that came in until the 80s, and that has caused that the soils became acidified. But luckily, we fixed the emissions, so we have no deposition of acid compounds anymore. And when we made the study with the large database and a model, then it's the gray one, we expected the forest to recover, the number of acidified forests to go down. Now I want just to remind you what this has to do with our energy. If a forest is acidified, the soil gets acid, then there will be more mobilization of aluminum. Aluminum is toxic, and with a certain amount of acidification, you start to get significant losses in growth. So very, very high losses in growth if the soil is acidified. That's why we lime, for example, certain soils. If we're going to produce biomass, we cannot have acidified soils because the trees will not grow as well. So we want the number of acidified soils to go down. If we only consider the deposition, then the number of soils should go down. But when we include this feedback of uptake, then the number of acidified forests goes up. And the reason is that we are taking away nutrients from the soil when we are, you remember that curve when the forest is growing faster and faster for the last 100 years? That means we're removing nutrients from the soil, parking them in the tree, and causes more of the soils to be acidified. On top of this, when we harvest, we don't allow the tree to die and return the nutrients. We take these nutrients out of the forests. We are impoverishing our soils, and this sooner or later will create problems. So this is the pathway now. When we have a higher nitrogen load, we increase uptake, we increase growth, and this causes more uptake of base cations, which is this that buffers the acidity in the soil. And this agrees with empirical data. So this is information from a very intensive network of survey called the Swedish National Forest Inventory. This inventory has around 17,000 forest sites, and every 5 years, each one of these sites is measured again. And what you can see here is it's divided into 3 zones: north, midwest, and south. And in the 3 zones, you can see how much nutrients are lost when we harvest different parts of the tree. So this is the dark lines are if we only harvest wood. The dashed ones on the top is if we harvest these branches, residues for heat. And there is also proposals to harvest stumps, to pick up the stumps of the trees and burn them. And the gray line here is the acidification from the historical acid rain today. And you can see that the size of acidification historically is as large or smaller than the acidification from harvesting different parts of the tree. So when we start to take also the branches, possibly even the stumps, the effect of forest harvesting, the loss of these base cations, the buffering elements from the forest ecosystem may be larger than what we have lost due to acid rain, which was a big, big impact. I don't know if you ever came across acid rain, but there is a large patch of forest between Germany and the Czech Republic that died. It's called the Black Forest because of acid rain. It was large areas of forest that were completely dead. You can Google it up later on, acid rain forest or black forest, you see. And now it's coming back, but not everywhere, this dead forest. So this is what we are doing to the forest. At the same time, there has been a large review of forest inventory data in all the European countries in a program called ICP Forest, Inter something cooperation program. for forests. So they measure the same thing all over the continent, and these are different species. And what you see here, everywhere you see a dark color, it means there is a deficiency of nutrient. And you can see phosphorus, for example, for Fagus beech and base cations is a problem. For oak, phosphorus is also a problem. Oak for the Mediterranean region is an important species. And then we have Picea, which is spruce. It's the most dominant species in the north, so in the Scandinavian countries and in Sweden. And here you see deficiencies in more or less everything. And the same for pine. So these deficiencies mean that eventually we will get reductions in growth. You get pathogen attacks. The trees cannot defend themselves against pathogens because they have nutrient imbalances. So this fast growth is in volume, but we don't know if it's going to be sustained in health of trees. And if the trees aren't healthy, they cannot fend off attacks, and they cannot, for example, survive winter frost. If the sap doesn't have enough phenols, it will freeze in the winter, and then you crack the bark and the trees get very sensitive to attack afterwards. And this is what we can also capture with the models. So this is over time. This line shows you the nutrition of inside the tree that we can trace with the models. And when you go beyond this green and the red line, it means you are within some type of imbalance of nutrients. And more of our forests are going to this. I can skip this here. Now we want to look at something else. So with this model now, we can simulate the nutrients in a very, very small detail between one tree and the soil the tree is standing on. And then how do we know if this works? So we compared the model, which is the blue staples, with measurements of the size of the forest, and they agree relatively well. And this is a blind run, so there is no calibration, because we want to see if the projections we can do with this model are correct. So then we used it to test something else. Now we know what we can do with the forest. We decide what type of management we do. Then there is something that we don't decide, but we know more or less how it's going to look, and that is climate. Now, forest is very well adapted to the climate it grows in. But we know that with climate change, that the climate isn't going to be the same. We don't really know exactly what the climate will be like in every place. But we are certain about one thing, that it's not going to be like it has been before. So that we're sure about. So we use the model to test what's going to happen when climate changes. And this is a simple calculation of if we harvest more, where it's red, we know we take in more nutrients than the ecosystem is able to put back. And we haven't put climate on this one yet. We're just upscaling to the whole of the country. This is a map of Sweden. And if we do only stem harvesting, we get some deficiency, but not a lot. So around this 20 to 40 microequivalent per square meter a year. In the south, where forestry is most intensive. It's extensive in the north, but not the high intensity because it's very cold up here. But if we do more intensive harvesting, then more half of the country is exceeding the nutrient budget that it can manage. When we look at the temperature and the change in climate, we get actually very mixed signals before we simulate. And here are the signals we get. So when you talk to climatologists, or people joke around in Sweden and we say, yeah, climate change isn't so bad for us because we get a little bit warmer climate. I don't know if you've been here, it's quite cold, and it's especially in the winter half year. We get a little bit longer growing season, warmer climate, growing season, longer, maybe we will get better growth conditions. There is also the first Nobel Prize won by a Swede. It's called, the person is called Arrhenius. And it's about the response of chemical reactions to temperature. So this is the Arrhenius equation for temperature response. And what this tells us is that we will get 20 to 40% faster biogeochemical processes. This combined with 2 to 3 weeks longer growth period should tell us we get more nutrients available, longer growth period, so the trees should be doing better. We should have more growth in the future. And we're going to go and test this. So this is just a look at the release of of nutrients from weathering. So we're breaking down the rocks, they weather out, and then we get these elements that the trees can take into their biomass. This is the base scenario, how much weathering is today, and these are two climate scenarios in the future. And I don't expect you to see a lot of difference between these, because there isn't much difference between these two maps. These are two climate models, just so for us to be able to capture the difference between the different climate model projections. Not much difference, not much effect on weathering. So I'll skip this one and go to here. And the reason for that is, the hint for the reason we can see in empirical data. These are two experimental forests in Sweden, one in the north, one in the south, both very productive. And what we did here is a series of experiments, so manipulations. C is the control, I is irrigation only, F is fertilization, and the purple is irrigation plus fertilization. N is fertilization with nitrogen only, the others is nitrogen and all other elements. What you see is, especially in the south, when we irrigate, that's when we get the most impact. That's when we get the highest growth. This tells us that already when these studies were made, and these were published in 2005, then we had water limitation, especially in the south. So this is not unusual. If you're in Sweden, you'd think we don't ever have water limitation, but we do. And the trees, the forests are already water limited. So when we take this into the future and we simulate with the model, water deficiency is going to grow a lot. So anything that is dark red is 25 to 40% more drought or loss in increase in water deficiency. In both models, one model tells us this goes all the way to the coast in the north. One tells us it's mostly the southern half. And this is the change in the carbon stock in the forests. And green means slightly higher. So in the north, we do get that effect of longer growth period, faster biogeochemical cycles. But for the majority of the country down here, we are not getting any, rather the opposite, we will get less growth. So all the expectations we had about we may be able to sustain the growth of the forest, to provide the biomass, to sustain this vision of zero emissions, are maybe not so sure. So we shouldn't bet everything on the forest. There is another aspect, and this is a spider diagram. Maybe you've seen them before. And what you see here is different services from the forest. Now, you can do any kind of combinations here, but here is soil organic carbon, which is the long-term storage of carbon, the acid neutralizing capacity, so the buffering capacity against acidification, nitrogen leaching, which is indicator of eutrophication, and what we harvest, dissolved organic carbon, so on. And what you can see, every line here is one forest management scenario. And you can see that there will be trade-offs. One scenario can give us more harvest, but it will give us lower long-term storage of carbon in the soil. It will also give us higher eutrophication. So there will be trade-offs if we decide to manage the forest in a way to get more harvesting. I'm just checking my time, yeah. Maybe we can look at these a little bit. So these are all different indicators. What you see here is projections of what will happen with different indicators when we have climate change. When we don't have climate change, the lower 6 is when we do have climate change. And here are different atmospheric deposition scenarios and different forest management scenarios. And what I want you to look at is just the bottom line here. So what this one tells us is, if we only have climate change, we look here at the indicator of biodiversity. It's one of the indicators we can produce in our studies to look at how it changes. Only with climate change, we will get around 35% of the vegetation community that is different by the year 2100. If on top of that we add air pollution, we get around 40%. And this effect is much higher than the management. So if you compare this line and this line. So some drivers of change of our ecosystems are beyond what we can control with forestry alone. And in this case, biodiversity. And this shows us that we have some severe changes ongoing, and we have observed this already. And what happens is that the climate envelopes change, the nutrient niches, ecological niches change, and of course the species who can be there cannot be there anymore. I think this is, for example, for the Mediterranean, extremely relevant because their climate change is happening very, very fast, and not many of the species will be able to adapt fast enough to be there. On a scale of 100 years. Climate is changing within that scale, but not adaptation. That takes a lot longer time. So back to the hedgehog and the fox. So we have a little bit of time for questions, as I was asked. If we count on this increasing curve, well, I think it's a bit risky. We know also that this increasing curve has left and is causing other impacts that are negative, which may come back as a balancing feedback to the ability of the forest to keep growing and producing biomass. So I personally am very skeptical of projecting a continuation of this curve. And honestly, about the whole role of biomass in the transition, the volumes of energy we use are enormous. Using biomass on top of all the other uses that we have today to substitute maybe is not the most sustainable solution. And so thank you for your attention, and I am available for any discussion or questions.
Okay, thank you very much, Professor Salim Beljazid, for your intervention. Any question? You can open your microphone directly, or you can do it through the chat if you want.
I can ask the question I just typed out. Thank you so much for your presentation. It was absolutely lovely, and we definitely need to spend more time on forestry and trying to determine soil acidity and how the soil is doing in different countries, especially in Africa. My question was about whether your topic of discussion was on how to reduce climate change through forestry, or if when you talk about biomass from forests, are these residues of the trees on the ground that can be used for biomass, or does it involve actually having to cut trees down to use them for energy?
Yeah, that's a very good question. So forestry is all about cutting the trees down. You know, that's the purpose of doing forestry. You plant the trees, you take care of them, you fertilize them sometimes in order to cut them down. So cutting trees down is inevitable. Now, when I showed you those curves, those figures with how much export there is and how much of the world market there is, it's to tell you that all of these stems that we now cut down, so this is the tree, it has some branches, we cut down these stems. They are very busy making money somewhere else. We're making paper out of them, we're making logs and a lot of exports. So there are a lot of interests in using the stems in a traditional way, in a conventional way. The forest industry invested 25 billion crowns last year in new sawmills. So they need these stems to come into the sawmill so they can get their money back. They invest like this every year. So you are completely right. What is left then? If the stems are already taken, what is left for substitution of fuel? The branches. So what you do is you cut the tree, you cut off the branches, and you take the stem, goes into this production line. Everything else goes then into substitution, into refineries for liquid fuel. They go into combined heat and electric burners. So you create heat and you create steam to turn turbines to make electricity. The difference is this. The stems contain not so much nutrients. It's a lot of carbon, a little bit of ash. The branches and the needles especially contain a lot of nutrients. They're not a lot in biomass, but for every one you take, you're talking 1 or 2 orders of magnitudes higher nutrient content than in the wood. And so we get even more larger losses of nutrients. Before we left the branches, so they decomposed and left the nutrients for the next generation. Now we're taking away the branches. So it's not, from an ecological cycle perspective, we're breaking this nutrient retention potential that any biome has. So it is very much about using the residues. So we will have no residues. It will be more or less like a farm. You take away everything.
Wow, thank you. And then just one more quick question. So we know that trees help with absorbing CO2 from the atmosphere. So how does cutting down trees affect the possibility of using forests to reduce or to help with climate change?
Correct. Yes, that's a very good observation. So trees are like a little bit like us. You know, when we're teenagers, we eat a lot, we grow fast. You know, that's when you get the strongest potential for carbon capture. The difference, though, is that, you know, we put it here and here. The trees put most of it in the soil. That's the most stable part. Now, what happens when the trees get old is that you start to accumulate, but not at the same rate as a growing forest. When you cut it, you reset the whole thing. So you reset the carbon capture to zero. The bad thing, the worst thing is that when you go back, you actually allow the soil to decompose faster because you have more nutrients available for the microbes. The trees don't take the nutrients. So the microbes are there. There's lots of sugar around. What do you think they do? They eat it all up. So we get peaks of release of CO2. And it takes more or less, if you plant a forest, it will take around 20 years for that forest to cancel that emission that you got after the clear cut. So 20 years just to cut even. And then whatever years you stay after, you start to capture more carbon. The trees themselves, when you harvest them, if you make paper, that doesn't have a very long lifetime. You know, life cycle may be of a year or 2 years, then it's back to the atmosphere. So you want to use the trees in a way that you do products that stay, don't go back to the atmosphere, like building material or something that stays. So you're very right. The trees are maybe the most potent tool we have biologically to capture CO2. We have now new technologies and so, but of what we know how to do. And we're not using them for capture as much as substitution now. And we actually don't know the answer. Is it better to leave them there and capture CO2? Or is it better to substitute CO2 emitters? We don't really have a clear answer.
Okay, great. Thank you so much. When I was in Africa, well, in Zambia a few years ago, I noticed that some forests were being burnt, and it kind of freaked me out. But they told me, well, that's the only way that the soil can be renewed and can grow and replenish. Is that true?
That is very true. So in managed forests, we have a problem with fires. Fires are very natural. They do occur. That's why many trees are adapted to fires. Many of the Mediterranean trees, we know they would not sprout, so the seeds will not come out until you have a fire. But what you want is often occurring fires. When you have very frequent fires, they keep the debris, not the soil carbon. The soil carbon is below the surface. They keep the debris low. If you have the debris low and the fire comes, there isn't a lot of flames. It doesn't get very hot. It doesn't destroy the roots. It doesn't burn the soil carbon. The problem is when we manage the forest and we repress the fire, then this debris starts to build up. You know, it's like you're gonna do a firework with a small petard, with a small poof. Now you have many, many, many of these. So when the fire takes on, then you have very intense fires. Because you have so much debris that can burn, kill the roots, burn down soil carbon, and maybe even kill the trees. So forest fires are a natural occurrence. It's nothing that the forests don't know how to handle. It's when we suppress them and we allow the debris to build up too much that they become problematic.
Okay, so but our California fires that we have in the US are not good, right?
You know, we're scientists, so we have the luxury of being able to say, I don't know if they're good or not. I can just give you facts. Okay. They're not good because people die and property is lost, of course. But fires are natural. Okay. Forest fires have to be left to work because many species, like I said, they don't resprout without. For biodiversity, you need this. It's an important component. even with forest fires, regular ones, you get a net sink of carbon in forests. It's when we suppress them, which is what the US has been very good at doing for a long time. Suppressing forest fires, you get a buildup of debris, a buildup of dry, dead branches.
And so a good follow-up to a fire then should be someone going in or people going in and picking up some of the debris, right? So that if another fire comes in, it doesn't go all the way down to the root. Am I getting what you're saying correctly?
Yes and no. So in Switzerland, they did an experiment for many hundreds of years. They went in their coniferous forests and collected the litter fall. You know, the dead needles, they collected them, used them as fertilizer. They have some of the most severe nutrient imbalances in their trees. If you take the debris out, you take in the carbon and the nutrients out. If you let it stay in the forest, decomposes or burns down in small frequent fires, the ash stays. So removing the debris removes also the ash.
Okay. Okay, great. Thank you so much. I really appreciate this.
Okay. Any other question?
I have one question. First of all, thank you for this excellent explanation. I'm economist, so I lack of scientific skills on this part, but I would like to understand if you know how this source of energy compares with other renewable sources of energy, and if it's not the best efficiency possible, how can we make it more efficient? Yeah, thanks.
Thank you. That's a very good question. So when we're talking about energy, we're actually talking about two types. We have the energy sources, and something that we're still struggling with very much as a species is energy carriers. So there is a lot of energy around. I mean, the wind is there and the sun is there. How do we capture this energy and how do we store it and carry it is what is the problem. So in wood and fossil fuels and so, you get the carrier with your source. I mean, in fuel, and when you say oil, the energy is stored in the liquid, or in the tree, the energy is there. You can carry it. And then why is this important? You can use it when you want it. So if it's wind, you can't tell the wind turbine, could you turn please, because we need to run a factory. It's not going to turn if it's not windy. We can't control. With wood and energy carriers that we can control, we can turn them on and off when we want. So that's one advantage. Wood is not very weak in energy, actually. It's like maybe between 3 and 7 times 1/3 and 1/7 the energy content of oil. 1/3 is a lot of energy. It's a lot. I mean, oil is very, very energy dense. And so if you have 1/3 of the oil, it's not a bad deal. It's a lot of energy stored in it, but it has to be dry. The problem with biomass is if you burn it wet, most of the energy goes into getting the water out because the water sucks all the heat to evaporate. So you need to make it dry. So there is a logistics question. For rentability, it's not rentable because you don't make money out of it because it's costly to collect all these branches. You know, you can imagine I pick one branch. They do this with machines and so. So it's costly. You don't get enough return. The logistics are complicated. You know, with an oil well, you drill the thing and then you pump from one pipe. Now you have 74,000 square kilometers and you go and collect the branches. So it's very costly. There is no return yet. But this is a trade-off and decision we have to make if we're standing in front of a climate problem. Maybe we have to do this investment. So it's not yet economically viable for energy on a large scale. When we do biofuel refineries, refining the forest residue, it's even less efficient because you have losses throughout the chain. So you have less energy in the end, but at least you get a form of fuel that you can carry in vehicles, for example. So it's all trade-offs everywhere.
Yeah, I imagine that it happened the same with oil in the past, right?
Yeah.
So it was not as efficient as it is today, but we had to do it because we need it, no? So yeah, it's another alternative. Okay, thank you.
You're welcome.
Okay, thank you. Any other question?
Yes, there is a question. I say thank you for the floor, and thank you once more again for the presentation of the teacher. But there is a problem in our country, in DRC. The Virunga National Park in North Kivu is one of the province of DRC, Democratic Republic of Congo. Okay, there is people who, for cooking or for having energy to cook, they use the forest. They use wood to make coal and cook with it, because electricity is somehow expensive, and there is metal gas in in Kivu Lake. But there is the problem of taking wood from the forest, from the national park, instead of extracting the natural gas from the lake. So there is also an oil field. There is an oil field in the Virunga National Park. So can you suggest to the government to accept to take oil from the park, or from the national park, or to keep on taking wood from the forest to cook? So there is somehow a paradox. Okay, they don't accept people to cut trees from the forest, and there is a fuel oil, or there is natural gas that can be extracted, but it is not extracted from the lake. So how to do to have energy efficiency in that part of our country?
Oh, this is a political question, Jean. So let me answer it in a way that I don't get. So let me be very factual, just pragmatic, okay? Yes. So to extract oil or gas is a large infrastructure investment.
Yeah. So
if you don't have investments to pull in power lines for electricity, I don't know if this is, especially in an aquatic ecosystem. So okay. This is one. For the other one, I am convinced from the things that I have seen that small-scale use by communities is not damaging. I am sure this forest is maybe exposed to illegal logging by people who have bulldozers. I mean, if you're gonna use coal or branches to cook your food, you probably don't have enough money to buy a bulldozer and go and clear up areas. I don't think these people are usually the problem. They are very good scapegoats because they can speak for themselves. So I don't think this is even a problem to, find a solution. You probably have more serious threats to your forest than the people cooking.
Okay, so, but do you see in our country, the most used energy is biomass?
Yeah.
I think that you know that. So people continue taking energy from forest. It is somehow damaging the forest, and that's why in my reaction about what is the planet's boundary that we have exceeded in our country, I think that land use change is the one that have been exceeded in my country, because most of the time people go and cut, and if you pass somewhere, you can see some images can show you that truly there is great damages on the ecosystem. So I don't know. So what is the good way to have efficient energy in our country? So can
yeah. So Jean, you have a forest in a very favorable climate. The soils are not very rich because they are very old, so you should not take away the leaves and so on. But in a tropical forest, you may have growth of 1 cubic meter growth, not standing growth. 1 cubic meter of wood per year per square meter. That's how much your forest can grow. So every year. So I cannot see numbers that will tell me that collecting firewood is a threat. I don't think that is, because just compare the numbers. I don't think you burn 1 cubic meter in a month for cooking.
So if you can imagine the population of the town of Goma has around 1 million of people, 1 million of people. So imagine 1 million of people taking woods, taking trees from the forest. Truly, for me, it is a threat. Huh? 1 million of people. I think
you already know the answer you want to have, so.
Okay, so I was just trying to imagine. So, but thank you so much for. Yeah.
Okay, any other question?
Yeah. Hello. Can you hear me?
Yes.
Thank you, Professor Salim, for the wonderful presentation. In the course of your presentation, you made mention of the planetary boundaries, and you said part of the boundaries we've broken is the nitrogen and phosphorus. In Nigeria, where I am from, most of our farmers depend on fertilizer, and this fertilizer, the major constituents are nitrogen and phosphorus. I want to get an understanding of if this breaking these boundaries mean that we have overused nitrogen and phosphorus. That's one. And if that is the case, what are the implications and the consequences? And what could be an alternative to that? Because agriculture is, to an extent, one of the things we do a lot in Nigeria. Thank you very much.
You're welcome. That's a very, very good question. And this is really in depth. It's an ethical question. So, you know, when we talked about this with nitrogen, phosphorus, and I said 4 out of 5 among us are synthetic, including myself. If we decide to close this, 4 people cannot get food. Okay, who's going to choose the 4? Who is it who's not going to get? So there is no answer to this one, is the honest answer. I don't know. I know the effects and I know things we can do. So what are the effects? Effect number 1, we have very high grade mines of phosphorus now, today, currently. They have an ore content of 30%, which means every ton that you collect from the mine, you get 300 kilograms of phosphorus. This is very high grade. That's why it's so cheap. When these mines run out, and they will run out within 5 decades at most, that's the calculations we have today. So maybe within your lifetime, probably not mine. So where do we go then? After these mines, we go to 0.3% grade. That's gold. That's gold mines is 0.3%. So maybe phosphorus is going to be as expensive as gold. Okay, so imagine. This is in 50 years. That's one. We will run out of the source of fertilizer. That's number 1. Number 2 is when we say the planetary boundaries are broken, is because we release most of these nutrients out in the ecosystem beyond what we eat. You know, when you fertilize in Nigeria, the largest majority of the fertilizer is not in what you eat, it ends out in the water. And this causes eutrophication, it causes many, many ecological problems. What is the solution? There are many solutions. We will not have time to go through many of them now. So when we do farming, we have selected species that invest most of their carbohydrates in the part we eat. It's usually the fruit or the tuber or the grain. Where did this investment come from? What did they give up? They give up on the roots. They invest less in the roots. Have you ever picked up a wheat from a field? They have these ridiculous tiny root systems. It's like, that doesn't make any sense. They can have those tiny roots because we selected them genetically and through selection. Also because we feed them so much nutrients that they have very inefficient roots that they catch something anyway. So number 1 is to revert to species that are good at mining for the nutrients themselves. This is one. There are other types of nutrients. I mean, this is very, very honest. I don't mean this as every time you flush in the toilet, that's a resource that you throw directly down the drain, literally. There are ways to use this better. Our ancestors did this. They sent the animals around and the animals came and slept in one place, and that's the place that they farmed next year. So there are many solutions that we can revert back to. Why are we not doing it? Because there are interests. There are interests who invested in these new grains. You can ask around the farmers in Nigeria, maybe it's going to be the same as many other places. The farmer doesn't own the grain that they're going to plant. The grain that you hold in your hand, you're going to plant is not yours. You're not allowed to save grain from year to year to plant it because there are interests in selling specific grains related to interest in selling the fertilizer and the pesticide. This is a very large question that you take up. It's a very important one, and I think it's one that we have to deal with as soon as we can, really, because it's, the impact of this 50 years is not far into the future.
Thank you very much, sir.
You're welcome.
Okay, thank you very much for your interesting presentation, and thank you to the attendees for your comments, questions, and congratulations. Another question? Is there another? Okay, thank you very much. We'll continue tomorrow. Tomorrow we'll have two presentations. A presentation about biomethane production case studies, and the second one about renewable energy auctions. So see you tomorrow here, and thank you again. Okay.
Thank you.
Okay.
Thank you.
Thank you, and bye-bye.
Bye, thanks. Thank you.
Thank you all.
Bye. See you tomorrow.
See you tomorrow.
Bye.